is theoretically justified by our computation ring theory. Right? It's very elegant. Okay. And then, based on this margin maximization principle, we'll formulate. Any question?
Sorry.
Okay. So we formulate our learning objective, right? So a naive learning objective will be, okay, I'm going to first calculate the margin for the current linear classifier, and then in the outside loop, we're going to maximize the parameters of our linear classifier, right? So you can see that the straightforward formulation will be a max-min problem. In the inner level, we're going to go through all the training examples to calculate the smallest distance, right? The margin is defined as the smallest distance between the training examples and the separating hyperplane. And then in the outside, we adjust the parameters of this hyperplane. Although this is a kind of like simple, but it's kind of hard to optimize because you're solving a maximum problem. Whenever you want to update your model parameters W&B a little bit, you have to go through an inner minimization procedure. You have to go through the entire training set. This is really costly. And then to simplify this optimization problem, we leverage an important property of linear classifiers. We discussed in detail in the last lecture. Here we just briefly review, right? So the key idea is that, okay, if you look into the entire space of W and B, they're actually redundant to represent the separating hyperplanes. Why? Because for the same pair of W and B, you can actually skew it up or skew it down with some positive number. If you multiply them by 100, 1,000, 1 billion, or 10 to minus 3, they all correspond to the exact same hyperplane, right? To separate the examples. Right? So it's unnecessary to search the entire space of WB to identify our optimal linear classifiers. Instead, we can restrict our search space to a small subset of WB. And what subset of search space should we use? Right? So we want to make our optimization procedure as convenient as possible, right? As we just mentioned, right? So because whenever we update WB, we need to calculate the margin. Then we need to go through every training examples in the training set and find the minimum value of this numerator, right? And by the value of this numerator, this product is also referred to as a function margin, right? So we want to minimize the function margin across the entire training set. This is really, really expensive. And then now we restrict our search space of WB in that all the WB in its small subspace will make the minimum of this function margin automatically be 1. That's the idea. In so doing, you know that because in my constrained WB space, this minimum value is 1, there's no need to go through the inner minimization step, right? You only need to focus on the maximization in outside. That's the key idea. So we have discussed why you just constrain your WB into a small subset such that the minimum value of this function margin is 1 is right. You don't lose any possible linear classifiers. We actually have discussed in detail, right? We write in the top in the blackboard and we show the mapping between any linear classifier outside that space and some point inside that space, right? So I'm not gonna repeat again, but just refresh your mind. So we don't lose anything, right? But the benefit is that, okay, by putting extra constraints, we do not need to perform the inner minimization procedure to compute the margin. Right? And then, based on this idea, we end up with our objective function. It's called hard SVM. Right? So, first, the training objective function is to minimize W transpose W, which is the square norm of W. Right? We put a factor half in front of it just for convenience. We'll see that later. And this is a minimization is equal to maximizing 1 over the norm of W, right? Maximizing is inverse is equivalent to minimizing the denominator, right? It's the same thing. And to ensure that your WB are inside space where the minimum of this numerator is 1, right? We need to put a list of constraints. That is, for every example, xi with I, we must count function margin at least 1. Right? And then, because the minimum of function margin is 1, you know, all the function margin is at least 1, meaning that their minimum value is 1. Right? That's the idea to code the constraint to describe the subspace of WB. We're going to search over. Right? So this is called hard fallback machine. Why? Because we require every example, the function margin is at least 1. Right? So it implies that you not only correctly predict the label of each xi, but also the score is not small. Right? If it is bigger than 1 or no less than 1, it just means, okay, this product, right, is also referred to as function margin. Right? This product, at least, is positive, right? Meaning that it makes correct prediction. At the same time, this product is relatively big, right? It cannot be like 0.2 or 0.3. Right? It must be at least 1. So meaning that, okay, those examples can stay away from the margin. But if it is 1, it means that just stay on the margin. Is it realistic? Yeah, I saw someone shake the hand. No, of course, right? It's too strong, right? So remember, we cannot define all the real-world training set are linearly separable, right? So for many training sets, what if they are not linearly separable, or even almost linearly separable? Meaning that, okay, you can always find like 2 or 3 points out of this data set which cannot be correctly labeled by your classifier. Right? In that case, you cannot find a feasible region for WB. Right? Meaning that you don't have a set of WB which satisfy all those constraints. Not to mention, you can solve that problem. Right? So of course, this is not what we want. We want a very robust linear classifier learning algorithm. Right? We want it can fit all kinds of problems, right? No matter what kind of actual performance it provides, but at least it can deal with those cases. Right? Cannot, I give you a data set and just tell me, okay, I refuse to give you any linear classifier. Right? This is not what we want. Right? So how can we address this problem? Right? So now it will lead to a most common used SVM formulation, which is called a soft SVM. As the name suggested, it allows some examples to violate the linear separability. Right? So how can we enable it? The key idea is that we want to introduce an automatic mechanism such that it can allow some examples to break into the margin. So take a look at this particular data set. Hello? Sorry, the microphone today doesn't work very well. So it allows some examples to break into the margin. Right? So if we look at this training set, right? So we can see that most of examples are linearly separable, right? But these 2 examples are not linearly separable. Right? Because of these 2 examples, you actually cannot find any linear classifiers which can well separate all the positive and negative examples. Right? So then, why not we just allow these 2 examples to be excluded? Right? So when we look for some linear classifiers which has the largest margin, right? We just exclude these 2 outliers. And if the remaining examples are linearly separable, we just find a classifier which can perfectly separate these remaining examples, and then with maximum margin. Okay. So you can see that this is kind of a trade-off. I allow some annoying outliers to be excluded from the training set, and I just look for classifiers to classify the remaining examples and maximize the margin. Okay. That's the idea. And of course, when you allow some outliers to be excluded when you maximize margin, those examples might be misclassified. Okay. So you're gonna probably increase the training error. Okay. So this is the trade-off. Okay. So if we contrast with the original generalization error bound, we see that, okay, by excluding these two examples, right, you can find a linear classifier which maximizes margin for separating the remaining examples. Right? Your BC dimension is still very small. Right? So you can expect you still significantly reduce this term. But at the same time, because you exclude them from finding the maximized margin classifiers, you might increase the training error. Right? But overall, as long as the summation of these two terms can be significantly reduced, you still win. That's the idea of the soft XVM. Any questions so far? I just want to give you guys an intuition, and then we'll talk about the technical details how to fulfill this. Is everyone good with this? Oh, excellent. Oh, okay. So now let us consider how do we allow extra flexibility, meaning that some of the examples can be excluded, meaning that they are allowed to break into the margin. So this is a hard SVM, right? So objective function is to maximize margin. Minimizing this square norm of W is equivalent to maximizing margin. So here, the constraint for every training example actually requires every example has a function margin at least one, meaning that must stay on the margin, on outside margin, right? So now, if we want some example to break into the margin, we need to relax the constraint here, right? So how do we relax? We're going to introduce a slack variable for each example. Say, for example, I, we denote the slack variable by CI. Now we modify the original hard constraint into two extra constraints, to another constraint. First, we want the function margin to be no less than 1 minus CI. And in addition, we want this CI to be non-negative. So we can see the choice of KCI actually determines if this example is included in finding a max margin classifier or excluded so that it can break into the margin, right? Which value of KCI indicates that your example is still included to be separated by linear classifiers and maximize the margin. Can anyone give me a sense? Remember, in the original hard formulation, hard SVM formulation, right, we require every example to be outside margin, meaning that when we include them in searching for the linear classifiers with maximum margin, right? And when we identify that linear classifiers, all the examples must be stay on or outside margin, right? So now I introduce a slack variable, right? So what choice of slack variable's value will be reduced to the original situation? And thought?
If the value is 0, because it reduces to the same.
Yes, exactly right. So you can see that if the CI is 0, meaning that this function margin is at least 1, right? It's the same constraint as in the hard SVM. Meaning that, okay, your example must stay on outside margin. Right? It cannot break into the margin. So it indicates that, okay, this example is counted when we search for a linear classifier with maximum margin, right? When CI is bigger than 0, I mean strictly bigger than 0, then that means the corresponding xi can break into the margin, right? It means that, okay, when we look for a linear classifier to separate the remaining examples, right? This example is kicked out. It's kicked out. Okay. It is not counted. So that it has freedom to break into the margin. Does it make sense? Any questions so far? Well, in ideal case, okay, we would like to say, okay, if all CI is simply 0, right? And now the constraints will be exactly the same as the constraint for the hard SVM. So all the examples must be well separated by the linear classifier and stay outside margin. Does it make sense? Okay. So now we turn our new optimization problem in this way. So first, in the constraint part, we relax the original hard constraint, meaning that every example has a function margin at least 1. Namely, the example stays outside margin or on the margin. That means when you search a linear classifier to separate the training examples, right? This example is counted. Why? Because I want to separate it and I want to maximum margin. And that means that example must be a stay on or outside margin, right? Remember, the margin is the closest distance. And right now, if the CI is not 0, it's bigger than 0. Bigger than 0 means that, okay, this function margin can be less than 1. It means that, okay, when I search a linear classifier, I exclude those outliers. So I only look for a linear classifier which can separate the remaining examples and maximize their margin. Right? So those outliers, well, they are free to violate the margin. They can break into the margin. They can even go to the other side of the margin, the other side of linear classifier, the other side of average. This is very important to understand the key idea here. Okay. But now let us look at the objective function. In addition to this regularization term, which is to maximize margin, we also add a summation of all the select variables multiplied by constant c. We're gonna go to talk about constant c later. But why do we need to also minimize the summation of the select variables? Any thought? Any guess?
So you don't just ignore all of the examples.
Can you say it again?
So you don't just ignore all of the examples by increasing their slack value?
Yes. Any supplement? Yeah, your point is 100% correct. It's very good. Yeah, but I want to illustrate more detail. So what if we don't append this term in objective? Right? I just minimize this square null, multiply constant half, right? And then with this multiply constraints, what's the consequence? We can think about that, right? if you look at this constraint, right, this constraints actually give you the flexibility. You can throw out a bunch of points. And then you just seek a classifier for the remaining points and maximize margin, right? So if you don't add this additional term in objective function, well, you can throw out whatever points you want. As long as for the remaining points, you can find a margin as large as possible. That's now good. Like, we can take a look here as our previous example. So if our objective does not consider that actual term we mentioned, right? So that means in the constraint, you are allowed to throw whatever training examples you want, right? You just look at the remaining examples and look for a max margin classifier. You can maximize margin as large as possible. Then what's the consequence? Right? What's the consequence?
I think in our formulation, you would always just set W to 0 and throw out anything that disagrees. Because you're minimizing W squared.
Let's just first not consider the actual value of W and K, but just from the points, right? From the geometry view. You can see that now that you have the flexibility to throw out whatever points you want, right? So now, in order to maximize margin for the remaining points, what points should I throw out? Will I throw out? And just pick the closest pair of 2 points, right? And just throw out all the other points. And then I maximize margin. I found a classifier to classify this leftmost point and rightmost point, right? And my linear classifier will have the largest margin, right? But at the same time, because I will all the remaining points as outliers, I don't care if I can correctly classify them or not. That's the consequence. Remember, in our objective, we still try to purely maximize margin. Right? And in a constraint, we are allowed to freely choose those examples, throw them out as outliers. Don't consider them. Then in order to maximize margin, why not just throw out all closed pairs of positive negative examples? So just choose one pair of positive negative examples, which are furthest apart. Right? And then I find a linear classifiers which in between, of course, I'm sure they have the largest margin. Right? It has the largest margin. But why? This is not good. Why is it not good? Yes.
You're only really learning 2 data points. Like, you're ignoring everything else. You're actually learning it line.
Yeah, intuitive, yes. But can we explain it based upon some theory?
You have a really large training error.
Yes, exactly, right? Look at the generalization error bound here, right? While doing that, although it sounds a little bit extreme, right? Well, you indeed reduce this dimension here largely. But at the same time, because you do not care about all the remaining points, you actually significantly increase the training error, right? So that basically means, well, remember, our generalization error bound is a summation of training error and this term determined by the basic dimension, right? You cannot just reduce this one while increasing this one. You must find a best trade-off between the two so that their overall summation is small. That's why we can't just maximizing margin. We need to account for the training error as well. Does it make sense? So now, if we take a look at our new objective, right? We add the summation of select variables. We actually encourage the summation of the select variables to be as small as possible, right? So remember, the select variables is not negative, right? The smallest value will be simply 0. When the select variables are 0, meaning that all the examples are satisfied the original constraint, meaning that they not break into the margin. Right? They do not break into the margin. They are all correctly classified. Your training error is as small as possible. Right? So now, we can see that the new objective function actually reflects the trade-off between the VC dimension and the training error. Right? The smaller this term, the smaller summation of select variables indicate that the smaller the number of examples that break into the margin, the smaller the training error. At the same time, I want to minimize this W transpose W, which indicates that I want to maximize margin. I still want to restrict my hypothesis space to be as small as possible. This is a trade-off. You cannot pursue one extreme case while ignoring the other. That won't give you the best compromise on each other. Okay, any questions so far in understanding the formulation of the soft SVM? Is everyone comfortable with this? Okay, great. Okay, so now let us look at our formulation of the soft SVM. Right? So soft SVM is very general formulation. It can deal with all kinds of data, right? No matter the data is really linear separable or non-linear separable or almost linear separable, at least solving soft SVM can give you a reasonable linear classifier, right? So in our objective function, we actually have two terms. As we mentioned, it represents a kind of like a trade-off between the basic dimension and the fitting of the trained data, right? So the first term, the square norm of W multiplied with half, is equivalent to a maximized margin. The second term is to minimize the total select variables. Right? So the minimization of the summation of these select variables indicates that we do not want to exclude many examples to search for the max margin classifiers. Instead, we want to as few examples as possible to evaluate the margin, meaning that I want my training error to be as small as possible. At the same time, I want to maximize margin. And then we're going to have a trade-off between the two terms. And this C is also called a hybrid parameter. Well, unfortunately, we don't have a method to optimize C. You have to manually choose that. Okay. And it varies. The best trade-off, the best compromise between the two depends on the particular problem or particular application. Right? So you have to choose them according to the specific problem. So okay, so I want to, before we proceed the optimization, how to optimize it, I want to confirm again. Any question regarding this formulation of the soft SVM? Okay. Yeah, everyone looks good, right? Okay. So that's really great. Because we spend quite a lot of time discussing the motivation, how we come here. At the end, you'll see that learning soft SVM in the primal domain, in the dual domain, is really simple. It's just writing down a constraint optimization problem. That's it. And then you can use off-the-shelf library to solve it. But the key is to understand why we can do that and why this works. That's the critical step. So you'll see that in your homework 4. For example, when you are requested to implement SVM, it's really simple. It doesn't need a lot of 1,000 lines of coding. You just need to know how to call SciPy optimization library to solve that. But you do need to know how this optimization is formulated. Why we got these two terms in our objective function, why we introduce this set of constraints. Okay? So now, when we solve this optimization problem, of course, although we just do a minimization, right, with respect to these constraints, this is still a little bit uncomfortable. Why? Because I have to deal with those constraints, right? And the most convenient way, we're gonna eliminate those constraints. Right? I want to do a free optimization problem, right? So I don't need to care about these constraints. I don't need to care about during my search procedure will I violate any of those constraints, right? So how can we eliminate those constraints? Right? So if you take a look, for every example, right, we have two constraints. One is about the function margin, the other is about the slack variable, right? So if you just made a small reorganization of this first constraint, we got that the slack variable is at least or no less than 1 minus function margin. Right? At the same time, the second constraint tells us that the slack variable is non-negative. So now we can see that the slack variables has two lower bounds. That means slack variables is at least bigger than or equal to the maximum of the two. Right? It must be at least no less than maximum of 0 and 1 minus the function margin. Right? So now if we take a look at the objective function. Right? So in the objective function, we want to minimize this term plus the summation of slack variables. Of course, if we can directly set Ci to be the smallest variable we can take, and then we don't need to consider this part, right? According to the lower bound of the Ci, the minimum value of the Ci is actually the maximum between 0 and 1 minus function margin. So now we just replace the Ci by the minimum value we can take. Right? So now we eliminate the slack variables, and the summation of the Ci now is replaced by summation of their minimum values, which is maximum between 0 and 1 minus the function margin. So now we end up with our formulation of support vector machines in the primal domain. So, any question regarding to this formulation? Okay. It's just made a simplification step. We just eliminate the slack variables. And you can take the smallest value of the Ci, which is the maximum between is 0 and 1 minus function margin, right? Because in the objective function, we minimize the summation of the Ci's. So why not just take the minimum value of the Ci? That will be the max between 0 and this one. And now our optimization problem becomes a free optimization problem. You don't need to care about any constraints, right? It will be much easier. Any questions so far? Everyone is good? And this objective actually has reflected some meaning. So we're going to talk about right now. So if we look at the second term, right, by replacing Ci by the minimum value we can take, right, we can see that this maximum between 0 and 1 minus function margin indicates the penalty of using the current model WB for the prediction. Why? We can consider three cases, right? So first, if the example xiyi can be correctly classified, and it's also outside margin, the value of this max is simply 0. Why? If you take a look, if the example is correctly classified, that means this product, namely function margin, is non-negative, right? That's what we discussed before, right? And meanwhile, if it is outside margin, meaning that this function margin is bigger than or equal to 1, right? So 1 minus something bigger than 1 will be negative. Max value between 0 and negative value will be 0, right? So the whole max outside will be 0. So in the very first case, okay, if your classifier can correctly predict xiyi, and also xiyi are kind of far away from the hyperplane. It stays outside margin, and then then this max value is 0, means that you don't need to suffer from any penalty. And the second case, if this example is not correctly classified, meaning that your product yi decision score is negative. And then you can imagine y minus some negative, it must be positive, right? And then this whole max value will be positive. So remember, we overall want to maximize, want to minimize the whole value, right? Now you give me a positive value, actually give you some penalty. So the value of the penalty will simply be the right term here, y minus the product here. So you can see that if you incorrectly predict between example, well, you're going to suffer from penalty. And third case is kind of a little special for support by machine. Even you correctly predict the example, but if this example is too close to your classification type of plane, you still suffer from penalty. Let's see the case, right? It is correctly classified. Well, that means this product, the function margin is not negative, right? However, if it is within the margin, means that function margin is less than 1. Right? Means that it breaks into margin, right? That's what we have just discussed. This product is bigger than 0, but less than 1, then when 1 is subtracted by this, it's still positive. Right? So this max value will be positive, which is still this. So meaning that, okay, even if you can correctly predict the example, but if your example breaks into the margin, then you still got some penalty. So when we summarize all the three cases, we can see that this max function over each string example actually represents a loss function, or cost function. It's similar to the square loss we used before, right? But in our least mean square problem, we use the square of the difference between your prediction and ground truth as the cost, or as the penalty. But here, things becomes much more complex, right? We got 3 possible cases. For each different case, we got a different penalty. So we call this loss function a hinge loss function. This is a very well-known loss function in machine learning. It's called hinge loss. This is max between 0 and 1 minus your product between the ground truth label and your decision score. It's called hinge loss. So give a more intuitive look at the hinge loss. Here we just show the figure of the hinge loss. So the x-axis is actually the product between the ground truth and your decision score, which is also referred to as the function margin. Right? So this black line represents the hinge loss, and those red line represents the 0-1 loss. So 0 loss, as the name suggests, if your prediction is correct, you don't have any loss, or you don't have any penalty. It's simply 0. If you make a wrong prediction, you're going to suffer a penalty, which is simply 1. So you can say that if you make a correct prediction, well, this function margin or the product is non-negative, right? So you can see that the 0 loss is simply 0. Otherwise, if it is negative, meaning that you make wrong prediction, the loss is 1. Now what if hinge loss? So you can see that hinge loss is essentially an upper bound of the 0 loss. So first, if your prediction is correct, and also prediction score, the function margin is large enough, meaning that the function margin is no less than 1. That corresponds to the case that your margin, your example is staying outside margin or out of margin, then your hinge loss is simply 0. You don't need to suffer from any loss. And in the second case, where your prediction is still right, because this product is non-negative, but the example is too close to the hyperplane. That is, the function margin itself is less than 1. You still suffer from some loss. you're still penalized. And finally, if you make a wrong prediction at all, right, the product you want and the prediction score is negative, but of course, you need to suffer from a large loss. Right? And also, the larger the error you make, right, the larger loss, the larger the penalty you're going to suffer from. Okay, any questions so far? In understanding this definition of the Hinge loss, just give you an intuition about the behavior of the Hinge loss. Okay. So now, by looking at the formulation of the objective, right, the support vector machine, we actually can see that the objective function consists of two terms. Right? One term is to maximize the margin, which is essentially to analyze the complexity of the capacity of the hypothesis space. Right? You want to favor a simpler classifier. Meanwhile, the Hinge loss term indicates how well you fit the training data. So this also reflects the two terms, the compromise of two terms in the generalization error bound, right? The training error plus a term determined by the basic dimension, or accordingly determined by the complexity of your hypothesis space. This actually reflects a kind of trade-off between two terms. And this structure also reflects an even more general learning strategy. The first strategy is called risk minimization principle. So risk minimization principle is just to care about how well we fit training data. So we define a loss over the training data, right? The learning is to find a hypothesis that has the lowest loss on the training data, meaning that I want to make my training error as small as possible. But this is actually not very good, because from the computational learning theory, it knows that the generalization error is determined by the training error plus the term dependent on the capacity or the complexity of the hypothesis space. Right? If I only care about the training error, well, I can use a very expressive, very complex hypothesis space, right? Or classifier. Well, I can get a smaller training error. But at the same time, the other term is increased, right? And overall, you still get a larger bound of the generalization error. So, a more robust, a better framework will be the so-called regularized risk minimization. So in a regular risk minimization framework, your objective should consist of two parts. The first part regularizes the complexity of hypothesis space, meaning that I want to penalize over complicated, over expressive hypothesis space. I want to favor a smaller hypothesis space. Right? Meanwhile, I need to define a loss over the training data to encourage your learned hypothesis has a small training error, as small as possible. So you can see that SVM is a typical instance of the regularized risk minimization. Right? So the first term, part of W transpose stuff, is a regularization term, which essentially to maximize margin and imposes preferences over a hypothesis space which is smaller and has a so that it has a better generalization performance. At the same time, the Hinge loss here penalize those classifiers which cannot well fit to the training data, right? They want to fit to the training data as good as possible. And here C is a hyperparameter that controls the trade-off between the two terms. And of course, if you want to design a new machine learning model and its training objective, you might choose alternative regularization terms and alternative training loss. Actually, this risk regularized risk minimization principle is widely used in machine learning practice. Like if you train artificial neural nets or train many other sparse models, you will always need to add some regularizer on the model parameters to avoid or fitting to favor easier and smaller hypothesis spaces. Okay, any questions so far? Is everyone comfortable? Great. So now we're going to talk about how to train the support machines. We're going to first start with the free optimization objective just mentioned. That is the regularized risk minimization one. But that won't give you a sense why support vector machines are called support vector machines. What do support vectors mean? So we're going to first talk about the training of support vector machines in the primal domain with the stochastic gradient descent. And then we'll introduce some basic knowledge about the optimization, like Lagrange multipliers and the primal dual transform, and then how can solve the dual form, and then we'll talk about how to solve the SVM in the dual domain, and then from that point we'll talk about where the support vectors come from, and then how do we inject the current trick we actually discussed before, so that we can extend SVM to very powerful nonlinear classifiers. So you won't worry too much about, okay, if your data is not linearly separable, what will happen? Okay. So this is, again, the objective of the support vector machines, right? So because this is a free optimization problem, you don't need to worry too much. You don't need to worry about the constraints. You can directly optimize with reading-based approach, right? So I have actually discussed about this and also practiced this a little bit, right? So everyone should feel comfortable. But of course, directly using the gradient descent is problematic. We discussed before, because to calculate one gradient, you have to go over the entire training set. Right? This is expensive when the training set is large. So for large data, we usually prefer stochastic gradient descent. But there's a bottleneck here. You'll see that the Hinge Loss used in support vector machines are not differentiable. You are not able to compute gradient or stochastic gradient for this. Then how should we choose a direction to update our model parameters? That's the problem. So we're gonna talk about the following topics. Right? So first, we're gonna review the convex function, concept convex functions and gradient descent framework to refresh our mind. And then we'll talk about the stochastic gradient descent framework for learning support vector machines. And then right now we can talk about more about the difference between the gradient descent and stochastic gradient descent, and what's their advantages and disadvantages. And then we need to address how to calculate the gradient for the Hinge Loss. Right? So it is not differentiable, so we're going to use a concept called sub-derivative or sub-gradient. We can use sub-gradient instead to update the model parameters, can still guarantee convergence. And finally, we'll talk about the stochastic sub-gradient descent framework for support vector machines, and then we'll compare with perception. So previously we mentioned that perception is mistake-driven algorithm, right? But later we'll see that at the end of this chapter, we're going to see that perception is essentially stochastic sub-gradient to optimizing another objective. This is really interesting. Okay, so first, let us look at the definition of convex functions. Right? So first, the conclusion for support vector machine is that this objective function is convex. It's convex in both the feature weight vector W and bias prime B. So this is really easy to show that. I'm gonna leave it as exercise for you, but I can just tell you that the first term is a quadratic term, is for sure the convex function. The second term, it's a composite function. Composite of max function and this linear function. So linear function is convex, and the composite max of the linear function will be convex as well. This is a basic conclusion for convex optimization. So if you're interested, just take a look at the textbook. But here, for convenience, again, we're going to use the notation simplification trick. We use the extensively, right? So we will fold our bias parameter into the weight vector, so that accordingly, we're going to augment the feature vector with a constant 1, right? To account for this bias parameter B. And of course, because in the first term, this weight vector is only weight vector, it doesn't contain the bias parameter B, so we denote the original weight vector, feature weight vector, by W0. So now, if I use this simplified notation, our objective function now is written in this way, right? So the first term is W0 transpose W0 half. Remember, W0 corresponds to the weights for the original features. It does not contain bias parameter B. And then in the Hinge loss, because the B is folded into the weight vector, so our function margin is W transpose Xi. There's an augmented weight vector and augmented feature vector. So don't be confused. We're gonna stick to this simpler representation of the objective. So now let us recall the definition of convex function. So the convex function is defined as follows. If for every input u and v in the domain, and for every lambda between 0 and 1, f is convex if this inequality holds for every u and v and lambda, right? So this inequality just tells us that if you evaluate the function as a convex combination of two inputs, so u and v combined with lambda, right? This function value is less than or equal to the combination of the function value at u and v with lambda. So I visualized the idea of this inequality before, right? So if you take a look at this convex function, here's two arbitrary inputs u and v, right? Any point in between can be viewed as a convex combination between u and v according to some lambda, right? So on the left-hand side, if you evaluate the function at this convex combination of the inputs, it's here. It's here. But if you evaluate the convex function of the function values, here, and then it will be here, right? So you can see that the convex combination of the function values is bigger than the function value of the convex combination of the inputs. That's what this inequality requires. If your function satisfies this inequality for arbitrary choices of u and v and lambda, and then your function is convex. Another very important property of the convex function is that if it is differentiable, then at any point, if you draw a counter line, then this counter line stays below the entire function value. So you can see this red line is the counter line at this particular point, x, right? And this red line stays below the entire value of the convex function. So this is reflected or described by another inequality. So f of x is the function value, right? Because this holds for any x, right? And the right-hand side is essentially linear function. Right? You can see this linear function, it passes through it's u and f of u, right? And the slope is the gradient of f at u. And here are a few examples of convex functions, like linear functions, or we call it convex functions, quadratic functions, convex function, and max function is a convex function. And here's a two-dimensional case. you can view as a special case of projective functions for two-dimensional inputs, while visually they correspond to the cone. And how to show a function is convex? Three commonly used strategies. First, just use the definition to show the convex inequality of this whole. Right? And second, if the function is differentiable, twice differentiable, you can just show the second derivative is always non-negative. And third one, okay, if your function is twice differentiable and it's a vector function, you can show the Hessian matrix is a positive semi-definite. But regarding how you get this, from this you end up with this convex inequality. This is not our scope of this class. If you're interested, you can take a look at any textbook about convex optimization. And if you change the direction of the convex inequality, right, you require that for a function, every pair of u and v lambda, your function evaluated at convex combination of inputs is bigger than or equal to the combination of the function values at u and v. So this set of functions is called concave functions. The simplest one would be just to take the negative of any convex function. It will be concave. Like this is minus x squared. It's concave. And its mean function, you take minus max function, its mean function is concave. And linear function is also a concave function. Why? Because for linear functions, this is not infinite, it's just equality. So it's satisfied for both convex function and concave function. Both convex and concave functions are a set of very small sets of functions. Actually, the most functions are neither convex nor concave. So these are neither convex or concave functions. Like sine functions, they're not convex functions, not concave functions. So what's the benefit of a convex function? Why should we repeatedly talk about convex functions? It has a very nice property, actually. The reason is simple, it's just because it has a nice property. For example, if you want to optimize an arbitrary function, if this function is differentiable, and then there is a necessary condition, meaning that if x is a minimum for a differentiable function, then the gradient of the function at x will be 0, right? Yeah, I believe everyone knows that fact, right? But is the opposite true? In other words, if I tell you, okay, here is an x, and the gradient of your function at x is 0, can you claim that x is your minimum of the function? Okay. The answer is no. Why? Because the function, the gradient 0, it might correspond to maximum function. It might correspond to minimum function. Right? So you can take a look at the curve here. At this maximum, the gradient will be 0, right? At this minimum, the gradient will be 0. And in an even annoying case will be the saddle point, meaning that it might not be maximum or a minimum. If you take a look at the function curve in this way, so at this point, if you take the gradient, it's also 0. But the value here is neither a maximum value or minimum. In other words, gradient to be 0, gradient being 0 is just a necessary condition for you to find a function minimum. Like if your function has a minimum x, well, the gradient must be 0. However, you cannot assume vice versa. If you find a point whose gradient 0 is not necessary to be a maximum, not necessary to be a minimum, is even not necessary. It might be not maximum nor a minimum. However, for convex functions, you don't need to worry about that. If you can find a gradient, a point whose gradient is 0, and it corresponds to the global minimum. And even better, so like functions like sine functions, cosine functions, they are vivid, right? You can view them. They might have many local minimums or local maximum, a global minimum, global maximum. But for convex functions, the local minimum is the global minimum, and only have one. You either have an infinite number of global minimums or only have one. That's the major benefit of convex functions too. It can avoid you verifying a lot of tedious cases. And some cases are hard to verify. If this minimum is a global minimum, that's why, if you're trying to learn artificial neural nets, while it converges, you can never claim that I converge to a global minimum. If it converges to some local minimum, you will okay, this is good. So now, if you take a look at this simple vector machine, we know it is convex, right? That's very good. And meaning that if we can find a minimum, and then it corresponds to the global minimum. And this problem is a classical problem, which is called quadratic optimization. Why? Because the objective function is quadratic, which is mainly embodied in W0 transpose W0. You can call any quadratic programming library to solve that. The problem is that this quadratic programming is quite slow. And you might stick to the gradient-based approach, like gradient descent framework, right? We have used them before, but it has the bottleneck as we discussed before, right? So every time if you want to calculate one gradient, you have to go through all the training examples in training data. Suppose you have 1 million training points, right? You need to calculate 1 million times to get one gradient to perform one update. This is really slow. So really, we're gonna seek for the help of the stochastic gradient descent. However, to look at the stochastic gradient descent framework, we need to first briefly review the gradient descent framework. I believe everyone is familiar with that, so just quickly review that. Right? So for arbitrary objective function, here it's just our SVM objective function, and you start with some initial guess of the model parameters denoted by W0. You just run many iterations. Right? Inside each iteration, you calculate the gradient of the objective function and the current model parameter. Then you update WT along the opposite direction of the gradient. Why? Because you want to minimize the objective function, right? And the gradient indicates the increase of the function. So if you want to minimize the function, you need to move along with the opposite direction of the gradient. This is the example we have used before to illustrate the idea of gradient descent, right? To optimize this function, to minimize this function, we start from W0, and the gradient is along the right-hand side direction, right? So you move towards the negative gradient direction, which is to the left, right? You get W1, then you get W2, you get W3, and we imagine that after a finite number of updates, you get enough close to the minimum of the objective function. That's the gradient descent framework, and we can immediately embed our support vector machine objective into the gradient descent framework. We initialize our weight vector with W0, then we go through many iterations, and suppose we are able to compute the gradient of the objective function at current WT, right? So let us just put aside the non-differentiable problem. Right? We just assume, okay, we are able to compute some kind of gradient, and then we update our weight vector as follows, right? And we subtract the current weight vector WT by learning rate multiplied with the gradient, right? R is called learning rate. And you do it again and again until you finish all the iterations, or some tolerance level is is satisfied, and then you finish the greedy descent. Right? So this is a greedy descent framework. So of course, greedy descent framework is not very favored by the large data set because it's too costly. So an alternative choice, a more popular choice, would be stochastic greedy descent. It arises in observation that if you compute the full gradient, you have to go through all the training set. So then why not, every time when I just pick one example, when I meet one example, I just calculate approximation of the gradient. I just update my model parameters, use this approximate gradient. Right? This approximate gradient is called stochastic gradient. So now let us look at how do we compute stochastic gradient for SVM. This is a little bit different from the linear regression problem. So again, the whole framework is the same. We're going to initialize our model parameters W0 to be 0. So remember, W0 here includes, this is a superscript. W0 includes both the model, both the weight parameters and also bias parameters. This is an augmented weight vector. Okay? And then we're going to go through big T epochs. Remember, each epoch is to say I'm gonna pass through the data once, right? So inside each epoch, every time I just pick a random example, xi, y, from the training set S. And now I'm gonna duplicate this example many times to make a full data set. In other words, I'm gonna fake a new data set with xi, y by simply duplicating them. To make sure this full data set has the same size as the original training set. And then I look at the SVM objective function on this fake data set, and then calculate the gradient. So that's the idea. So on this fixed data set, well, the objective, of course, includes this regularization term. And then, because we duplicate this particular random example for big N times, here N is the number of training examples. So when we calculate the loss or calculate gradient, we do not need to really calculate N times. We just calculate 1, just multiply it by N. Then I calculate the gradient on SVM objective on this fixed data set. Use that gradient as my stochastic gradient to update the model parameters. That's the idea. So here's the key step here. Remember, it's we need to repeat the random chosen example x of yi for big N times. That is equivalent to create a fake data set which has the same size as the original data set. And then I calculate the objective on this fake data set. Of course, it is much easier. And then take the gradient to update the model parameters level. So someone may ask, why do you fake the data set? Why do you repeat them for N times, right? So now at least the mean square regression problem seems that we do not need to do that, right? You just take an example randomly, and then you just calculate the gradient, right? Stochastic gradient. You never need to fake the examples or repeat examples, right? The reason is that in our SVM objective, we have an actual regularization term. Remember, in the original SVM objective function, right? There are two terms. One is regularization term. The other is actually the loss over the entire training set. You need to maintain the same scale. You can now, okay, I just calculate one example and just calculate this particular loss over this example, right? Actually, you've got imbalanced scale for the two terms, right? They actually need to maintain the scale of the loss term and the regularization term. In doing that, you maintain the right scale, then your stochastic gradient will have the guarantee. Does it make sense? Any question? Or someone might be curious to know why, in theory, right? This is not the scope of our class, but I list the derivation here. So basically, if you fake the data set, meaning that you just duplicate examples for big N times, you fake a data set, then you calculate the gradient. It is equivalent to calculate the gradient here. Right? So here, R value is the half of the square norm, and then this N is number of training examples, L is loss. Right? So if you calculate this gradient, you can show that the expectation of this gradient is the exact gradient. So remember, the gradient here, here is random. Why? Because your xi, yi is randomly something. Right? So y is called, this is why it is called stochastic gradient. And in so doing, you can ensure that the expectation of your stochastic gradient is the exact gradient. And if your expectation of the stochastic gradient is the exact gradient, it's called unbiased stochastic gradient. Then the theory of this stochastic optimization will guarantee you to find a minimum of the objective function. But this piece of slides is just for reference. It's not required to know how to derive them and to better understand. But I mean, very intuitively, you can view as, okay, I want to maintain the skew, right? If you just calculate one loss over this xi, yi, well, you actually lose the trade-off of the skew between W0, transpose W0, and this whole loss. You need to multiply by n to maintain the right skew. Okay, any questions so far regarding the framework of the stochastic gradient descent for SVM? Okay, next we're going to continue. We're going to finish up this on Thursday.